Hi everyone. So we had a few technical difficulties in the live session today, so we didn't get to cover question 5. And since a couple of you asked about question 5, I thought I'd record a short video just to show you where to start from. So question 5a asks to state the quotient rule for the identification of tensors. Okay, so the quotient rule is straight from the notes, so you can just look up the notes for that part. But 5b, let's think about that. So 5b asks you to prove that if Tij xi xj is a scalar for an arbitrary contravariant vector x, xi, then Tij plus Tji is a tensor. Okay, and it tells us that this isn't actually a trivial application of the quotient rule, because the quotient rule says that you have to have an arbitrary tensor, but in this question we're given the tensor xi, xj, and that's not the most general second rank contravariant tensor. Okay, so we want to prove, so the question says that if Tij, so a covariant rank 2 tensor, times with an inner product of xi, xj, if this is a scalar, this is a scalar if xi is an arbitrary. Okay, so the question says if this is a scalar when xi is an arbitrary contravariant vector, then prove that Tij plus Tji is a tensor. Okay, so I'm just going to give you a couple of hints to start, but I'm not going to go through the whole thing. So the first thing is that it's telling us that Tij xi xj is a scalar. And if this thing is a scalar, then if you think about it, this implies that Tji xi xj is also a scalar. Okay, and the reason being, the i's and the j's are dummy indices, so we can call them whatever we want. We can have t cat dog, x cat, x dog. Okay, doesn't matter, we can change them. So we can swap the j and the i's, so we can write this as t ji xj xi. Okay, so here we've swapped I to j and j to I. But then it doesn't matter what order we write these things. Okay, so this is equal to xi xj. Okay, so this is Tji. Okay, so if this is a scalar, then so is this. Okay, so if this is a scalar and this is a scalar, then we can add them. And of course, the solution of adding them is also scalar. So Tij plus Tji xi xj is also a scalar. Okay, and this thing is a symmetric matrix. Symmetric covariant rank 2 tensor. Let's call it Mij. Okay, Mij xi xj, this quantity, and we know that it's a scalar. Okay, so the question asks us to prove this thing, which we've called M. Prove that M is a tensor. Okay, so what we do is we use the fact that we know that Mij xi xj is a scalar. What does that mean? If it's a scalar, then we can transform to a coordinate system and the result is the same. So we can write M bar ij x bar I x bar j. This is this quantity in the new system, and it's a scalar. Because it's a scalar, there are no partial derivatives, d by dx's, etc. It's just the same quantity, Mij xi xj, the same form. Okay, so in the old coordinate system, it's this. We transform coordinates. It takes the same form. We just put bars on the top, and that's because this whole thing is a scalar. Okay, equals because it's a scalar. Okay, so remember, a scalar is a rank 0 tensor. Okay, so you have 0 powers of the Jacobian derivatives. Okay, so from here, it's just a matter then of considering how the x's transform. Because the question tells you that xi is an arbitrary contravariant vector. Okay, so from this point, you just think about how x bar is written in terms of x. Dx by dx, and there's a bar here with an I and a j and an xj. Okay, and you just substitute this in and then keep going. Okay, and that's all I'm going to show. There's still a few subtle bits after this. Okay, so hopefully that is helpful.